Hi, greetings. I'm Neil. Welcome again. This chapter is on magnetic force, Faraday's Law of Induction, Hans Christian Ørsted work, and a host of other things. It's a lengthy chapter, but it's a phenomenally important chapter. Look at this beautiful picture here of the city of Denmark, Copenhagen. Copenhagen in Denmark. This is the site of many things. It's a beautiful city. It's a very walkable city, and highly encourage you to go check it out. I had a great time there. At the University of Copenhagen in 1820, Hans Christian Ørsted made a startling discovery. While giving a lecture to advanced physics students, Hans Christian Ørsted, he discovered that a compass that was nearby an electric circuit, as he was giving this demonstration in class, whenever he turned on the power in the circuit, on or off, the compass needle gave a deflection. Two separate things, unattached, seemed to be linked together somehow. Well, much later on, it came to fruition that we now know that while Hans Christian Ørsted was turning on the current in a circuit and turning it off, that was altering the magnetic field that the current was producing in the circuit. And that magnetic field was distorting the compass needle. If the compass needle got deflected to the right, for example, when the current was turned on, and as soon as it turned off, the compass needle got deflected in the opposite direction, so it went back and forth. Funny thing though, if the current was flowing steadily in the circuit, the needle and the compass showed no deflection whatsoever. So that was also peculiar. There was only a noticeable deflection when the current was changing. That is to say, a changing magnetic field was being produced. And that changing magnetic field was causing a distortion in the position of the compass needle. So this is the birthplace of what we now know as the field of electromagnetism. We owe a lot of this to Hans Christian Ørsted's work. So in this chapter, and it's a lengthy chapter, the reader's going to get quite a bit of information over here. This is where it all happened. City of Copenhagen. I highly encourage you to visit. It's a very, very beautiful city here. We also talk about the Biot-Savart law. French physicists also around that time, they came up with a derivation, an expression, or an equation, if you will, to calculate what the magnetic field is due to a current in a wire. Now that we know that currents produce magnetic fields. So the law is dealt with, and several examples are shown how we can calculate what the magnetic field is at any point, really, due to either a long straight wire like I've dealt with here. I worked this out as an example. It looks relatively complicated, but it's not. It just takes a bit of patience on the reader's part to pay attention to the details as I've derived it here. And it's an easy to use application, this Biot-Savart law, to calculate what the magnetic field is due to electric current. I've also done it for a curved wire, so I've taken that straight wire and I've curved it so we can see how the angular component plays a part in determining what the magnetic field would be. So much calculations to keep the reader busy for quite some time. I've done several applications of this. I've also derived the force on a current carrying wire due to a magnetic field. That is to say, let's just say you've got a circuit and there's a current flowing through one of the wires, and the current fluctuates over time, so it's producing a magnetic field that's fluctuating. That magnetic field is also producing a fluctuating force on other nearby current carrying wires. So if there's a current in the nearby wire, there's a force on that wire due to some prevailing magnetic field in the vicinity. It sounds like it's really not useful, but I assure you it's very useful. So I've derived the expression for this, how to calculate the force on a current carrying wire due to the presence of a magnetic field. And it's not a terribly difficult derivation, and the reader can have a go at it. But the significance of that, though, it's beyond far-reaching. Virtually every facet of life, from security to medicine, technology, electric motors are involved. And what I've just described to you was the principle of the electric motor, a force on a current carrying wire. So I've dealt with that, how the electric motor works in this chapter. It's essentially a looped wire with a current running through it, placed in the presence of permanent magnets, and the magnets produce a constant force as the current in the wire changes direction because it's looped, and that creates essentially a perpetual motion machine, if you will. So electric motor is derived from the force on a current carrying wire in the presence of a magnetic field. It's quite fascinating. Again, the applications are absolutely numerous. One of them was I had read an article about, this is in Krakow, one of my trips to Europe. I went to Auschwitz, the concentration camp, the former concentration camps of Auschwitz. This is the actual gas chamber that was used in Auschwitz. I'm standing in the gas chamber, and I took a tour around the grounds of Auschwitz, outside of Krakow in Poland. And I read an article where the barbed wires that were meant to keep people in there, they also ran electric currents through the barbed wires in opposite directions. And so parallel wires had opposite facing currents. And I thought about this. I don't know the authenticity of the article, but it was, it's interesting to think about. And so I did. I came up with an example of this to calculate, the benefit of running. Well, not the benefit, but the significance rather of running a current through wires in opposite directions, like not just for this situation, but for high tension power lines that transmit, current and voltages over vast distances, from the plant to people's home and substations. So this, if we consider these two wires over here with current running in opposite directions, what it does, it turns out, as I was able to show in this real-life example, that it wasn't just keeping the wires taut, it kept people from pulling them apart who were trying to escape, but by running the current in opposite directions, the magnetic field produced by one of these wires was opposite in sense to the magnetic field produced by its neighboring wire. That's say if you took a wire, and this is called a right-hand grip rule, and if you were to put, consider your thumb along the direction of the current flow for your right hand, then the fingers, they wrap around the direction of the current. Your thumb points in the direction of the current. Your fingers tell you the direction of the magnetic field. So if you got one wire with the current running this direction, the field is going to go this way, and if you switch it, the field is going to go the other way. And those two fields, they act like a north pole and a south pole in between the two wires, and it creates an attractive force pulling it together, a torsional force that's pulling it together. So it keeps the wires even more taut, makes it even more difficult to pull it apart. So I calculated what the additional force and the tension would be, keeping those wires from moving apart. And it's interesting. It's a measurable force, a very small force, but it is non-negligible. It's still measurable. So I thought that was an interesting example of a real-life situation, or a former real-life situation. This chapter also talks about Ampere's law. Ampere's law deals with calculating the magnetic field due to multiple currents flowing at the same time. It's a relatively simple rule to apply, but it's also very, very useful. It also uses the right-hand grip rule as well, and the reader can pay attention to that in the course of the chapter. So several examples have come out of this. This is Alcatraz Island of San Francisco Bay in California, infamously known as a prison from which no one escaped successfully that's known of. There was one attempted escape by 3 men, but they never found any remains or any information leading to the authenticity of a successful escape. So as it stands, that's still up in the air. If you make it to San Francisco, you can go across the Golden Gate Bridge. You can see it's shrouded in mist and fog. It's perpetually shrouded, and it's only the rare days when it's not shrouded. And so that water on those metal cables that's holding up this bridge, it's like a magnet for lightning strikes. So I've done several examples of using the Golden Gate Bridge and lightning strikes and how much current would run through these metal wires. And so, what would the magnetic field be as a result of the current from a lightning strikes that get conducted along the cables holding up the bridge? And it's actually quite interesting. And so the reader can have a look at the derivation of the different values of the magnetic fields and the currents that would go along the Golden Gate Bridge. Should you go visit, it's something you can say you've got some knowledge about. Finally, Faraday's Law of Induction from Michael Faraday. Turns out that changing the magnetic field through a coil, if you've got a coil and you alter the magnetic field, that is, if you took a bar magnet and you send it through or you pull it out, this induces a current, an electric current in that looped wire. This is Faraday's Law of Induction, and it kind of shows you how it works here with a closed loop of wire connected to a galvanometer. As a magnet is plunged into the cross section of the coil and removed, as long as the magnet is moving, the magnetic field in the cross section of the coil is changing, and that induces a current in the wire. So this is Faraday's Law of Magnetic Induction. And such things as the velocity of the magnet moving in and out, that is how quickly the magnetic field is changing in this loop, affects the magnitude of the induced current as well as the cross-sectional area of the coil. That also affects the strength of the induced current. And the application of Faraday's law are quite numerous. Things like transformers, for example, step up and step down transformers for alternating current and direct current signals are all dealt with. And this is how power stations, they transmit power, because it's energy efficient to transmit power over high voltages. And when they get to a substation, they are dropped down from about 100,000 volts to about 5,500 volts. And then eventually, when they get to your neighborhood transformers on the light poles, they step it down to 120 volts. So these are applications then, these transformers of Faraday's Law of Induction. And there are several other examples. This is some Christmas lights in Germany, a Christmas market that I was taking a tour of during Christmas time. Came up with some examples of the magnetic field that was being generated in the vicinity of all of these Christmas lights. It's actually a pretty cool example. I thought was interesting. You never think that Christmas can get this complicated, but it was actually a good example. And to round off the chapter, a bit is said about Maxwell's equation. James Clerk Maxwell, the British physicist, somewhere around the year 1831, his crowning achievement was to link electric charges, electric fields, magnets, and magnetic fields all together in a system of 4 equations now known as Maxwell's equations. So the importance of these equations is really the basis for all of electromagnetism and all forms of communication, for that matter, radios and stuff like that. It was a crowning achievement, and the reader can have a look at this in the chapter. There are 4 equations, and it's sort of the umbrella of equations for everything that has to do with magnetism and electricity. And even the speed of light, believe it or not, is wrapped in here. This is the brilliance of Maxwell's equations. So we'll leave it for the reader. So I hope you find it interesting. Once again, I thank you for your time.